So in our last video, we left off with this slide on atomic orbitals, and today we're going to look at, in this video, the um, way that we can denote the location, or the address, as I like to call it, of an electron. And so we do that by using these things we call quantum numbers. I want to pick up again where we left off in the last video. The last thing I talked to you about was how we represent the orbital shapes, the electron cloud shapes. And we represent them with 4 different letters. So there's 4 different cloud shapes. The letters that we use are S, P, D, and F. Now each of those letters correspond to a specific shape. The s orbital is spherical in shape, and so you can see here that it is a sphere oriented around an imaginary XYZ axis. This, if it were a 1s orbital, if I were to ask you to draw a 2s orbital, it would still be spherical, but it would be larger. So I'll kind of outline here around this. It would be a spherical shaped orbital, but it would be a little bit bigger. The 3s orbital would be a little bit bigger sphere than that, and so on and so forth. Then we have the p orbital. Notice the p orbital sort of looks like a figure 8 here, and this is called the p sub x because notice it's on the x-axis. But I always remember the shape of the p orbital because to me it looks sort of like a peanut. So think about what a peanut would look like, and it would sort of look like a figure 8. So this is your p orbital. Remember, p for peanut. Then we have our d orbital. This is a little bit bigger orbital. And if you look at it, you'll notice that it is like 2 of the peanuts together, so I call it a double peanut. Here's one figure 8, and here's the other figure 8. But it's like 2 peanuts together, so it's a D for double peanut. And then finally, the last type of orbital is an f orbital. And the f orbital is sort of like 3 of the peanuts put together. So I remember F for flower shaped. If you look at this and think about a flower, I'm going to draw it a little bit differently. So here you have, think about that as a flower. If that were like the bloom of a flower, here you go. You get F for flower. Some students just remember that it's the fancy orbital shape. It's the fanciest one. So we have the S, P, D, and F orbital, and we're going to be talking a little bit more about how to represent those orbitals shortly. But these are the 4 cloud shapes. I want you to think about these cloud shapes sort of like the houses that the electrons are found in. And I use that analogy because we are talking about how to locate the address of the electron. And so if you think about your address, you have a specific kind of house you live in. You have a street that you live on. And so we're gonna talk about these quantum numbers and relate them to our addresses to hopefully make it make a little bit more sense to you. So now let's talk about the 4 quantum numbers. There are 4 of them, and each quantum number kind of gives us a clue to the address of the electron. Now, in order to fully understand the address, you have to have all 4 quantum numbers. So we're going to talk about each one individually, and I will say this can be a little bit confusing at first, and it won't make a whole lot of sense until all 4 numbers have been explained. So just kind of bear with me, and at the end we'll recap with a summary of the 4 quantum numbers and the patterns on the periodic table that you can follow to find your quantum numbers. The first quantum number is your lead quantum number and is called your principal quantum number. So look at this word principal and think about our principal of our school is the leader of our school. So I remember the principal quantum number is the lead quantum number. And this is the very first one you find. The symbol for the principal quantum number is a N. Now N, the principal quantum number, is always equal to the energy level that you find your electron in. So I remember N is the symbol, and it tells us the energy level. N, focus on the N, energy level. Now, if you look at your periodic table, if I were to ask you to draw a Bohr model for any given element, the way that you would figure out how many energy levels to draw around the nucleus is you would look at the period on the periodic table. So the N quantum number is always equal to the period that you find your element in. It tells us the amount of energy that the electron possesses. And since we have 7 periods on our periodic table, N can have values equal to 1, 2, 3, 4, 5, 6, or 7. Again, the N quantum number for any given element corresponds to the period number on the periodic table. As N increases, so as the value for your N quantum number increases, the distance from the nucleus also increases. So let's consider this Bohr model for an atom. If this black dot in the middle represents your nucleus, and you see the pink spheres or circles around it represent each energy level, notice we have 7 energy levels here. So the N quantum number would mean the electron is on the first energy level if it was N equals to 1. If I told you N equals to 2, then we're talking about an electron on the second energy level. If I told you N equals 3, the electron's on the third energy level, 4, 5, 6, and 7. So the N quantum number corresponds to the energy level you find the electron in. And I sort of think about this when you relate it to your analogy of an address, sort of like the street that the electron lives on. Now notice as you go higher and higher to your N value, as you get a larger N, then you have a farther distance from the nucleus. The lower the N, the closer the electron is to the nucleus. Let's look at the second quantum number. The second quantum number is also known as the orbital quantum number or the azimuthal quantum number. You can just remember orbital quantum number. The symbol for the orbital quantum number is a lowercase cursive L. This is an L, not an E. The orbital quantum number tells us the shape of our orbital. The values for L can range from 0 all the way up to N minus 1. Now remember, we just talked about N, and N is your principal quantum number. So the values for L do depend on the value for N. Every quantum number is dependent on the quantum number immediately prior to it. There's actually 4 values for L that we need to be familiar with. The first value for L is 0. If L equals 0, that corresponds to an s orbital, always. Remember, the s orbital we learned is spherical. So S for spherical. If L ever equals 0, you're talking about a sphere-shaped orbital. Now, I've always remembered this value because if you trace a sphere, then you have a 0. That's the number you would have drawn. If L is equal to 1, that's always corresponding to a p orbital. So remember, the p orbital is the next shape. That's your peanut-shaped orbital. If L is equal to 2, that corresponds to a d orbital. So that's your double peanut-shaped orbital. And then finally, if L is equal to 3, that's representing an f orbital or your flower-shaped orbital. Now, in just a little bit, I will share with you how I remember the the numbers for L, 0, 1, 2, and 3. But for now, let me just suffice it to say that it's the order that we learned them, the shapes in, S, P, D, and F. But the orbital quantum number tells you the shape of the orbital. Remember, the shapes are the sphere, peanut, double peanut, and flower, or SPDF. So every quantum number L corresponds to a shape. The third quantum number is called your magnetic quantum number. And the symbol for the magnetic quantum number is M, a lowercase m. M tells us the orientation of the orbital around the nucleus. The values for M range from negative L to positive L. As I said earlier, each quantum number's values depend on the quantum number immediately prior to it. So since L came right before M, the values for M depend on what L was, and the values range from negative L to positive L. Now, before we look at the actual values, let's talk a little bit about the shapes. So we said that if you look at this, this is your s orbital. So notice this is a spherical shaped orbital. The second row here shows the different orientations that the p orbital can take around the XYZ axis. I want you to notice there is one orientation for an s orbital. There's only one way that you can turn a sphere, if you think of it that way. No matter how I turn the sphere, it's always spherical. But with the p orbitals, there's 1, 2, 3 orientations. These are our peanut-shaped orbitals. Notice this one here on the far right is aligned on the y-axis. We call this the p sub y. This one is a p orbital lined on the z-axis. We call that p sub z. This one is lined on the x-axis. We would call that p sub x. So the p orbital can take 3 different orientations along the nucleus of the XYZ axis. So the p orbital always has 3 orientations. I'll put ditto marks for that. There's 3 orientations. Now, the d and the f orbitals get a little more complicated, but the d orbitals, I want you to notice, these are your d's. There's 1, 2, 3, 4, 5 d orientations they can take around the XYZ axis. So they have 5 orientations. And then finally the f orbital, here's our f orbitals, 1, 2, 3, 4, 5, 6, 7. They do get more complicated with the d's and the f's, but I want you to notice the pattern. One for the s, 3 for the p, 5 for the d, and 7 for the f's. You are not going to have to draw all of these different orientations, but you do need to remember the s always has 1, the p always has 3, the d always has 5, and the f always has 7. 1, 3, 5, 7. So remember, starting at the number 1, counting odd numbers. That's going to tell us, these orientations, how many boxes to draw in just a few minutes, because we're going to draw the orbital notation using boxes instead of all these fancy shapes. So now let's get to the notes. So we're going to look at the orbital letter and possible orientations that I just introduced you to. The possible m values, remember they go from negative L to positive L, and we're going to look at the box method last. So I told you the S has 1 possible orientation. So if you think about what we learned about the S, so I'm going to come over here and remind you of the the L value for S. So we learned on the second quantum number L that the L quantum number for an S orbital is L is equal to 0. And I told you the way that I remember that is because if you draw an S orbital, a sphere, And then if you were to trace it, the number you would have drawn is a 0. That's how I've always remembered the L quantum number is 0. There's only one way to turn a sphere. So you would draw one box. The p orbital. Now, the p orbital has 3 orientations. Now remember, I told you the L quantum number for a p orbital, L is always equal to 1 for the p's. But the values for the m quantum number, which is what we're talking about now, go from negative L to positive L. So if L is 1 and you count from negative 1 to positive 1, think about a number line, you would write down negative 1, 0, and 1. Notice there's 3 numbers here. Those correspond to the 3 orientations that I just mentioned on the last slide. The P on the y-axis, the P on the x-axis, and the P on the z-axis. Instead of drawing the 3 orientations, we're just going to draw boxes, and I'll show you in just a second what I mean by that. The d orbital. It has 5 orientations, so there are 5 different ways it can position itself along the XYZ axis if it's a double peanut orbital. Now remember, the d orbital's L quantum number that tells you the shape is L is equal to 2. So if L is 2, then m goes from negative 2 to positive 2. So notice negative 2, negative 1, 0, 1, and 2. Those are the 5, 1, 2, 3, 4, 5 different orientations, but these numbers correspond to those orientations. Finally, the f orbital. We said for the f orbital, L is always equal to 3. These are the L quantum numbers. Since L is 3, the values for m can range from negative 3 to positive 3. Negative 3, negative 2, negative 1, 0, 1, 2, and 3. Now, I told you we were going to draw the box method rather than all the different shapes because the box method is going to be easier. So when we draw our boxes and do our examples, and we'll do the examples actually in class tomorrow, but when we draw the box method, I want you to always draw the boxes. So the S has 1 box, the P has 3, the D has 5, and the F has 7. Draw your boxes and then number the boxes from negative L to positive L. So as I said, if L is 0, the only box you can number is 0. There is no such thing as a negative or positive 0, it's just 0. If L is 1 for the p orbital, you would go negative 1 to positive 1. So negative 1, 0, 1. And I call these my mailboxes. Remember, we're talking about an address here. We're trying to figure out what the address is for an electron. This m quantum number tells us the mailbox number. So if we're trying to get a letter to each element, we would need to know the mailbox number. The d orbital has an L equal to 2. So negative 2, negative 1, 0, 1, and 2. And then finally, the F has an L equal to 3. So we're going to number our boxes negative 3, negative 2, negative 1, 0, 1, 2, and 3. So these are the way that we number our boxes for the m quantum number. Now, as I said earlier, some of this is not going to make a whole lot of sense until we get the whole picture. So I've talked about the n quantum number, I've talked about the L quantum number, I've talked about the m quantum number, and now we're going to look at the s quantum number, the 4th and final quantum number. The s quantum number is called the spin quantum number, and the symbol we give for that is an S. What the spin quantum number tells us is it tells us the direction that the electron is spinning. See, electrons can either spin clockwise or counterclockwise. There's 2 different directions it can spin. So that means the possible values for the s quantum number are either going to be positive 1/2 or negative 1/2. If it's positive 1/2, that means the electron is spinning clockwise. So think about a face of a clock. And so if it's positive 1/2, the electron is spinning clockwise. If it's a negative 1/2 spinning electron, that means it's spinning backwards on your clock face, so it's spinning counterclockwise. Now, the way that we represent our electrons in our orbitals is we use arrows. If we want to represent a clockwise spinning electron, we always put an arrow pointing up, and that means that the electron is spinning in a clockwise direction. If we want to represent an electron spinning counterclockwise, we would put an arrow pointing downward, and that represents that electron is spinning counterclockwise. Now, you may be wondering, why is the value 1/2? Like, why is it not a whole number? Well, the reason is because in each of our orbitals, we can only fit 2 electrons. And think about it mathematically. 2 halves make a whole. So you can put 2 electrons in each box, each mailbox, and when they pair up, they have to pair up with opposite spin. Now, I call these husbands and wives. It's very important for you to remember that they pair up always with opposite spin. Each box must have 1 electron pointing up. I call that my wife, before they can pair up. And when they pair up with the second electron that's pointing downward or spinning counterclockwise is called the husband. So the electron points up, that represents the wife or a clockwise spinning electron. If the electron is pointing downward, this would be the downward pointing electron. That would represent the husband. They've got to pair up with opposite spin. Now, before we look at the periodic table, I'm going to scoot back to one little thing that we talked about, which is the box method, and I want to just show you how you would fill the electrons in the boxes. Every box can hold 2 electrons, so the maximum number of electrons that can fit in the s orbital, there's 1 box, 2 electrons per box is 2 electrons max. For the p orbitals, there's 3 orientations, so 2 can go here, 2 can go here, and 2 can go here. That's 6 electrons max. So how many could fit in your d orbital? 2, 4, 6, 8, 10. And how about your f orbital? 2, 4, 6, 8, 10, 12, 14. Now here's one last thing you need to know before we ever talk about how to actually find all 4 quantum numbers. And this is the fact that when you're filling in your electrons, if you're in the s orbital, I said that the up arrows are the wives. The wives always come home first. So you would always go wife and then the husband. The husbands cannot come home till all of the wives are home. So let's consider the p orbital. You have 3 boxes here. In order to fill these boxes up, these orbitals up, the wives all have to be home before the husbands. So you would go up, up, up. That's wife, wife, wife. And now the husbands are allowed to come home. Down, down, down. So if you're going to put all 6 electrons in those boxes, you would have to go up, 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 down, down, down. And there is a name for this rule, but we'll learn about it in a later video lesson. All right, let's look at the d orbitals. There's 5 total orbitals here. And so let me just say, if you were to determine you only had 7 electrons to put in these d orbitals. Now 10 is the most it can hold, but that doesn't mean that they're always full. So let's just say if you have 7 electrons, you would go up, 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 up. 5 went up, and then down, down, 6, 7. So there's 7 electrons, but when you fill them up, 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 down, down. If you were going to do the f orbitals, you would always go up, 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 down, 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 down. Now that is very important for when we start doing the examples in class next time we meet. All right, last thing before we conclude this video lesson, um, I want you to consider your periodic table. And I want to talk about each quantum number we just learned about to recap. So N was your principal quantum number. Remember, that's your energy level. So if you're looking at your periodic table, N always tells you the energy level, and it corresponds to the period on the periodic table. Then we talked about L. L is the shape of the orbital. Now, if the orbital shape is S, P, D, or F, that corresponds to a specific, what we call block on the periodic table. So we'll look at the blocks shortly. M is the next quantum number. It tells you the orientations. It's where you draw the boxes. Draw boxes. Then you're going to number the boxes. And then S, you're going to determine the spin of the electron. And so we're going to look at tomorrow how to label our periodic table with the blocks, SPDF, the N, energy level quantum numbers, and then the M and the S. So I'm going to conclude this here at this point, and this is all for today.